It wasn't me, Mike. I didn't do it.
So we'll talk through a couple things. Orbital capacities we'll walk through and kind of look at the electrons that could go into each orbital. Then we'll look at valence electrons. I did just post a video this morning. I recorded it Friday with the intent of posting it Friday, and I entirely forgot about it.
It's okay.
But that video walks through valence electrons, which is kind of a big part to get started into the Lewis structure. But based on the number of hands being raised about Lewis structure, hey, didn't matter because nobody watched it. So I will say it takes practice. And if you were previously taught Lewis structure, you were probably taught wrong. And you were taught in such a way that I know where it will fail, and I ask those questions. Just so you know. PhD means a fat load of nothing. It means you found 4 people that were willing enough to sign their names to a piece of paper. That's about what a PhD means.
Thanks. I didn't just finish that or anything.
I'm not saying that the content of a PhD doesn't necessarily be that, but there's plenty of loopholes. So,
and some people get PhDs,
been there, done
but
that.
teach classes that are only sort of related.
Yeah.
For instance,
So,
you can have a PhD in literature, but be teaching rhetoric, and that can be a problem.
Back to our conversation. Orbitals contain only 2 electrons. So if I take a look at the first energy level, I only get one orbital type, the S type. I can refer to that one specifically as the 1s. First energy, S type. How many electrons can I put into that orbital? 2. So if we were to fill this thing out, we could then write 2. Super exciting. How many electrons then fit in that energy level? 2. Which literally just counted for them. It's only 2. Okay? What happens if I move to the second energy level? Well, in the second energy level, I copy the previous orbital type, so I will also have an S type. So I will have the 2s. I have to identify it as different because it's in a different energy level, so it's 2s. And I add one more type. What is that one more type?
2p.
I get the 2p. Took the words right out of my mouth, actually. How many electrons fit in the 2s orbital? 2. How many electrons fit in a single 2p orbital? 2. Why'd you say 2? I said a single 2p orbital. A single 2p orbital holds only 2 electrons. How many 2p orbitals are there? 3 2p orbitals. If each one can hold 2, I get a total of 6 electrons. Okay? How many electrons fit in the second energy level? Well, the second energy level is anything that had that 2 in front of it, right? Which means 8 electrons. First energy level on the periodic table. Sorry, I'm going to push button. Nope, I can't push buttons. Never mind. First row on the periodic table has how many columns in it? First row. The row would be the horizontal, also known as a period or series. How many elements show up in that first row? 2. How many electrons in the first energy level? 2. What happens when we move to the second energy level? We now have 8. Magically, how many electrons? 8. Okay. How many elements show up in the third row? 8. So what do you think is going to happen when we go through and move to the third energy level? It's going to be the same. So let's walk through it. Our third energy level, we copy what we previously had. What did we previously have? We had S and P, so we get 3S, 3P, and 3D. Every time we move up in energy, we add one new orbital type. The This might already be causing some people to panic a little bit here when they propagate this further out. How many electrons fit into the 3s? 2. How many fit into the 3p type? Type? 6. The question has changed. We get 6 electrons. How many fit in the 3d? 10. How many total electrons fit into the third energy level? 18. Anybody see something weird? When we move to our periodic table, you'll notice that third row does not have 18 elements in it. It only has 8. So what happened? So one thing I did here was, well, maybe this was flawed. Isn't the D the fourth energy level? No. Okay. The D orbitals absolutely come in at the third energy level. We absolutely did that right. So what does that mean about our periodic table? When we look at our D block starting with scandium, what's the energy level? It's the third energy level. Why is that weird? It's in the fourth row. The D block is offset by 1. Okay? That offset is a bit tricky. Okay? And where that offset is going to come from has to do with the fill pattern, how we place electrons into the orbitals. Okay? When we fill up the 3p, what element would we end at? Argon. Okay. Third row, fill the p, we'd end at argon. I add one more electron. We might say that it goes to the 3d. One more electron from argon would be? Potassium. Okay, officially with one more proton, but don't stress. Potassium is in the fourth row, yes? Which block is it? S. It's not the D block. The periodic table doesn't fill perfectly sequentially. Okay? We get these weird pseudo-exceptions, and at least people like to treat them as exceptions. There's a very good reason for why it doesn't fill perfectly. Okay? And we'll look at that in a second. We've organized the periodic table to show the fill pattern. Okay? That is why the D block is aligned where it is, offset by 1 after calcium. Because if I'd place scandium in the third row, I'd go from magnesium with 12 electrons to scandium with 21. That makes no sense. Okay? So I could take the scandium, mother fudge knuckles, put it over here. Argon plus 1 electron would be also not scandium. Okay? So I cannot place the D block in a appropriate section so that it matches the energy levels if I want to maintain information about how the electrons fill the orbitals. So it comes down to which is more useful. Do I want to know where the electrons exist, or do I want to make sure those blocks align arbitrarily with those rows? Okay, I want to know where the electrons exist. I want to know that proper fill pattern because that proper fill pattern is what allows me to use the elements and predict how they react. Arbitrarily matching rows and lines isn't a big deal. Okay? So that does mean, for your sake, anything ending with D elements or D orbitals, you have to recognize is offset by 1. Which means yttrium, Y, is going to be what for its outermost electron? It is in the D block, so it's definitely D. It's the first column of the D block, so it'll be D1. The energy level, so the row it is in, we would say 5th, but we have to remember it's offset by 1. And we make it 4D. Kind of, sort of? Okay. That fill pattern is on the periodic table. Okay? Yeah, we're just going to advance through that. Next part. I'll double back to that. That fill pattern, you can look up things like this that show how to properly fill. You write down all your orbitals, you align them out, and then if you've sewed before in your past, that's what they're trying to show here. This I find completely useless, okay? And it's not because it's bad, it's actually really good at showing the fill pattern. But the problem comes with how I'm going to write this down. Dang it, I'm starting to slide by an angle.
Some things are out of your control, like that.
Was that Greg? No. You could just blame Greg. What happens if we start writing this down? We're going to start slanting as we write. At least some people do. And if you slant, your stitching process now doesn't work out so nicely. Okay, that's why I don't like that. I remember seeing this in high school, actually, oh, that's awesome, and I can always do that. And I always effed it up because I kept writing on an angle and the whole thing went to hell. Okay? So while that is useful, that can show it. The periodic table also shows it. The first electron goes where? Hydrogen. First row, so 1. Which block? S. So 1s, first column of that block, so 1s1. I fill the S. Okay? To move up to the next one, what do I have to do? I have to go to the second row, first column, or the second column for that matter. The periodic table shows the trend. The one where it gets a little wonky is when we bring in the d orbitals. We have to remember the d orbitals are offset. As soon as we know the offset, I don't have to draw in straight lines. Right? If I don't memorize the offset, I have to draw in straight lines. Kinda?
Yep.
Okay. So let's backtrack a little bit here. A little bit more. Here's the rest of that slide. We got our 18 electrons. We could move up to the 4th energy level. We could potentially get 32. Okay? Notice there's the F orbitals coming in again, which means they should show up at the 4th energy level. Our F block was an inset. Is it showing up at the 4th energy level? Nope, it's offset. Why is it offset? For the same reason the d orbitals. It's now offset by the d orbitals and it's offset by the f orbitals. Okay? We don't have to stress about the f block quite as much because we don't use them that much. Okay? For the sake of this class, we won't use them at all. Okay? If you move into 151, I've seen a few test questions that people have written that ask for electron configurations of those. Okay? I can't count that high, so I don't ask that. Okay? Like 2 people got that joke. Thank you. Yeah. And you've heard it like 4 times. Okay? So let's look at our energy levels. First energy level, second, third, fourth, right? Blue, black, blue, green, yellow, etc., right? Okay? When we fill up, we go black, 1s, 2s, 2p, 3s, 3p. And we might say, well, then don't we go into the 3d? Okay? Well, what happens? We're going to have to color code this a little bit differently here. That yellow band we're going to make orange so that it actually stands out on the screen. That orange one's going to subdivide out. And actually, I don't know why I'm going to hand draw it because I've got it neatly done. Okay? It subdivides out into the S, P, D, and ultimately F, which I didn't draw on there. Right? Our first electron went the first energy level. Where'd the next electron go? Went to the first. Why did I not go higher? That's a higher energy jump. I fill the lower energy states first. Once we fill the 3p, okay, and this is going to get really, really small, but here we go. All these things are filled. These ones can be a little bit bigger. Right? They're all filled up. I've now filled through my 3p. Right? Where's my next electron go? Whoops, filled the 3d. Okay. If we look at our diagram, we're talking about placing it in the 4s or the 3d. What is the difference in energy between those two orbitals?
Very small.
Okay. The closer to the nucleus, the larger those gaps are. The further from the nucleus we get, the gaps in energy get increasingly smaller and smaller and smaller. That difference in energy is now so small, another factor contributes to the placement of the electron. Okay. For those of you that stuck around after class, on Thursday, you now know the argument. Okay. So let's clean this up. Let's get rid of all the stuff we don't need. We don't care about any of that. There we go. We're just talking about those two systems, either yellow or green. Okay, where should I place that next electron? Oh, what? What did you just say? It was an oh geez win when I drew this one. Why are you making that statement about this one? It's lopsided. You just made a judgment call about this. You were making that statement that that smiley face was ugly. Because it's not symmetric. Guess what? Chemistry does the same thing. Okay? And for those being like, well, those are just smiley faces, it's not a big deal. The example I usually like to do is that I have everybody close their eyes. You'll understand why here in a second. For those of you who will be like, no, I'm going to fight through this. Okay, you'll get the reason why here in a second. Yeah, close your eyes. Imagine the most attractive person you know. This is why you had to keep your eyes closed there. It's very awkward. Okay? If you covered half of their face and did a mirror reflection across, guess what you find? They look almost the same. Okay? There are memes, you can open your eyes again. There are memes out there, people doing, look, they look like freaks. That's because the picture was not a symmetric picture. Okay, you try and reflect someone's half face across onto a quarter face, of course it's not going to look right. Okay? But the most attractive people, classically, across all cultures, have symmetric features. Okay? The same thing is happening within chemistry. Which is more symmetric? One orbital with one electron in it, or 5 orbitals with only one electron? One with one. That is a more symmetrical system. That effect is a very minor effect. Okay? I don't know why I've never used the word before. An aesthetic effect. Okay? That is such a small effect that it really only matters when we get orbitals that are so close in energy that we don't achieve it. Okay? Or that difference in energy is so minuscule it's not a big deal. Now symmetry becomes a big issue. In the previous cases, the jumps in energy were so drastic that we just accepted the mole. Make sense? We're like, mole? Yeah, don't worry about it. Different reference, different audience. Maybe. Okay? That's kind of our defining system. Does that make sense? That weird kind of exception, we don't have to memorize as an exception because the periodic table tells us how it fills. It fills 4s before it fills 3d. Kind of make sense? Okay. So, we could go through and draw this diagram out every single time we wanted to fill things or fill out electrons. Okay? Or we could memorize our fill patterns. Okay? When it comes to what you are responsible for doing, you're responsible for looking at electron configuration and being like, that is correct for that element. Okay? We keep that relatively simple as far as multiple choice variance. So if I wanted to know, say, which of the following is the correct configuration for carbon, oh, geez. That was done pretty quickly. Well, let's go through and walk through it. I asked for carbon. The periodic table holds all of this information. Right? So carbon. Which energy level? It's in the second energy level because it's in the second row. Which block is it in? P block. Which column? We've now just explained the last electron configuration for carbon. Okay? Row, block, and then this is block column.
Is it suddenly easier to make your cryptogram? Yeah.
Okay? The rest of them are filled. So let's go through and look at our answer choices. Is the first one right? No. Did I fill them yet? I haven't even shown it. First one's wrong. Second one? Wrong. Third one? That fits. Last one? Wrong. Do I care about anything in between? Okay? At this level, we want to make sure that you can fill that last part. If you move up into 151, we're going to expect more knowledge. What's that more knowledge? Can you make sure the rest of it is correct? And you'll see variances within there. Even then, we'll get some simplifications that we could run through. That upper superscript represented what? Officially or not officially, it represented the block column for the last one. But what about that? That too. What does it actually mean? It's the number of electrons. Right? The 2 in 2p2, that superscript 2 that we're calling our block column, is the number of electrons it takes to get to carbon within that block. So when I look at 1s2, what is that 2?
2 electrons.
That is 2 electrons. What is the next 2?
2 electrons.
What is the next one?
4 electrons.
How many electrons is that?
8.
8. How many electrons does a carbon atom have? 6. Does that match? No, that answer is wrong. Okay? Those superscripts are the number of electrons. They need to match for the element you're trying to identify. Okay? Kinda, sorta?
Yeah.
Move to the next one. 2, 1, 3. Gets me? 6. Oh, that's carbon, so that must be the answer. It's both pieces of information. It's not just that we have 6 electrons, but that we've placed the electrons correctly. Make sense? Okay. So that is useful to pull from our electron configurations. I just set you up with like the backhand entrance to solving a multiple choice test. Yes?
So, like, will there be any questions that are like, what's the electron configuration from boron to carbon, to calcium?
Okay. Would I ask for what are the electron configurations from boron?
Like one element to another?
Boron, let's do boron to fluorine. Okay. To ask that question, how many electron configurations do I need to give you? Boron to fluorine. You need boron, you need oxygen, you need carbon, nitrogen, fluorine. A single answer means 5 different pieces of information. If it's a multiple choice, I now have to write out 25 different electron configurations. Could I ask that? Yes. Would any instructor in their right mind want to ask that? No, that's a lot of typing out for us to go through and do. Okay? What could be asked along those lines is what orbital is filled for the elements from boron to fluorine. So what do you think? What orbital is filled for the elements boron to fluorine? 2, they're in the second energy level. Fantastic. So 2s. No, because they're in the p block. So the answer is 2p. Does that make sense?
Not filled though.
They're in the process of being filled. Yeah. There is a question like that. I don't know the exact wording on it, but it's something along those lines. What orbital is I want to say is being filled for aluminum to chlorine or sodium to magnesium.
Does that basically just mean what orbital is being shared between those two?
You're not sharing orbitals. Don't do that. Sharing is now bonds. Okay. So what we're looking at is that when I go through and do the electron configuration for aluminum, its outermost electron is what? Aluminum. Third energy level, P block. So the outermost orbital is 3p. When I fill silicon, its outermost electron is 3p2. Is that still the 3p orbital? Yes, I'm still filling the 3p orbitals.
Oh, I get the question now.
Does that make sense, William?
Yes, but I was just breaking down the wording, like which blocks are filled with the
I apologize, Greg.
right?
I know that we are paired with an English class, and for that, I try my best to watch out for wording to avoid confusion like that.
Okay.
There is no guarantee that that's not going to be the case. Okay? So if you see something, you're like, well, but if this wording is interpreted this way, it means this. What should your response be? Raise your hand during the test and be like, this says ED as opposed to S. That is a verb conjugation, and that verb conjugation changes the meaning from this to this. And I'm going to be like, knock it off. Don't do that. Okay? So, yes and no. What you have to be doing is looking at the simplest explanation. If you have to dig deeper and you get it wrong, and so that's where the next big kind of point comes in, which is a big thing that I try to drive home for students. Defensible positions. I tell you to post the completion screen for PlayPosit, not because I want you to post the completion screen for PlayPosit, but if something fails in the process of me getting that information, what do you now have? A defensible position to say, I did the assignment. Okay? Now, as an instructor, I have to say, well, I'm not giving you points because I don't have it, in which case you have a defensible position to either challenge me or further up the food chain. Okay? So if you encounter a question on an exam, you should absolutely ask. Okay?
Especially if the answers aren't matching.
And if your answers don't align, and it's super rare for that to happen. But after the fact, you can come back and be like, this was my position. This is what I interpreted. Okay? Typically, what you were interpreting had some big flaw within it, and you weren't right anyway. So that's why it's a good idea to at least make that statement and make that argument.
And if you're nitpicking a test question and in the way that Mike's kind of saying, keep in mind the writer, like whether it's his class or it's somebody else's, if they're not, most teachers can write generally, but it's not their area of expertise. They're just they have a communicative purpose, they're trying to get through the test question, and that means that just like you, when they have their purpose isn't to always be grammatically correct. Sometimes the purpose is to get you to interpret the question. So if a language thing makes it confusing, remember who the audience is. If it's a writing instructor, it's possible they made a mistake. It's also possible they're really trying to get you to fine-tune language. If it's a chemistry instructor or someone who's not as into writing, there are a couple ways you can deal with that. And the best way in Mike's class is to say, hey, Mike, is this what you meant? So think communicative purpose. It's not likely that he's trying to trick you with language.
Right.
Carbon, because this is the next part for moving into Lewis structure. What we now want to do, now that we understand where electrons exist within an atom, I want to know what happens when I make a molecule. Okay? So if I take two atoms and I bring them near each other, and I'm going to try and come up with how a bond would form, and potentially what is a bond. Okay? I'm going to bring those two atoms near each other. What is the first thing that is likely to interact?
Electrons.
The electrons. So I am concerned where the electrons exist and how those electrons can interact between the two atoms. Which of these electrons would be most likely to interact for carbon? Okay. So those of you throwing out key terms, that's awesome. Stop using science.
The last V outside. To the outside.
Okay. Maybe it would help if we flipped back to this diagram and we looked at our electron configuration. Which of those electrons is most likely to interact with another atom? Remember, our nucleus is here. What we're describing is where's my pen? There it is. The sphere going around. Which electrons are most likely to interact? The ones on the outside are the most likely to interact. The ones on the inside are so deeply embedded in the atom and identifying that atom that they aren't likely to contribute. Which means, at least to a first approximation, I can ignore those. Okay? And what we end up establishing here is a difference between valence and core electrons. So I heard a lot of people give me these. Yes, those are absolutely going to be involved in bonding. But so are these. Okay? Both of those are going to be my valence electrons. Why? Those are the highest energy level. Okay? That bonding principle we're using is the highest energy level. I don't care necessarily what orbitals they're in. I just want the highest energy level. Okay? How do I know they're the highest energy level?
Because of the 2.
Remember, the number in front was the energy level. 2 is larger than 1. They're both 2s, so they're both in the second energy level. They will both count. So when I look at carbon, carbon has a total of 4 valence. I look at the superscripts that come after it, and we get 4 valence. Carbon also has those 1s, which will be referred to as our core electrons. Okay? They're embedded on the inside. We don't interact with those. Okay? So let's try bromine. 35 electrons. That was a bit dumb, but we already started. Our outermost electrons for bromine. It's in the P block, so we don't have to worry about any offsets. So it's in the 4th row. It's in the P block. It's the 5th column of the P block. Oh, it is. I did actually say that right. Okay. And I get 4p5. What else has to happen? I now need to backtrack through the rest and fill everything else up. Okay? So as we back through, cool. I heard 3D, because if we're backtracking, the very next thing that we would encounter, the very next block in reverse would be our D block. Remember, our D block was offset, so that's 3D. 3D what? 10, it's all full. The next one.
4s2.
4s2. Next one. 3p6. 2. Do we have a way to check this to verify that we did this correctly?
Yeah, the numbers have to add up to 35.
4, 8, 8, 10, 5. So that 12, 20, 30, 35. Cool, we did it right. Okay. Valence electrons. Valence electrons are our highest energy. Is there a number larger than 1? Yes, we've got 2. That is also in our electron configuration, just for clarity's sake. Okay, is there a number larger than 2? Yep, I've got the 3. Is there a number larger than 3? Yes, I've got the 4. Is there a number larger than 4? No. So 4 is our highest energy level. How many electrons in our 4 energy level? 7 valence. Can anybody do that? Somebody started to do it. What was it? 28 core electrons. Okay. That was our 35 minus the 7. For those of you being like, wow, that was fast math. I agree. Thank you for coming up with that number for me. Okay. Do we care about the core? Not really. Okay. You could theoretically see questions about it, but it's very rare. So 7 valence. So this means to find the valence electrons, what do we need to do? Write out our electron configuration. Whichever one had the highest energy level, sum those numbers, and we've got our valence. How many of you are happy with valence electrons? Yeah. Electron configurations. Happy. If I ask you to do it, you're like, yep, I'm good. Give it to me. Okay, so the rest of you are like, what? Do I really have to do that? No. No, you don't. Where's bromine on the periodic table? Okay, 35. Where was carbon? 6, right? Everybody remember carbon, the valence electrons? How many do we have? 4, right? One person remembered. That's good. The rest of you could check your notes because you were writing it down, right?
Yeah.
I know it's really small, so those of you on the other side of the classroom can look at the other periodic table. Those of you in the middle, you're just screwed. What is the Roman numeral, the top of the carbon column? 4. How many valence did carbon have? 4. That's just random blind luck. Bromine, totally not at the top of the column, so it must not work at all. The Roman numeral for the top of bromine? 7. The valence electrons are literally written on the periodic table. They're embedded in the Roman numerals. Remember when we talked about families and we said lithium, sodium, potassium, rubidium, cesium, francium all reacted the same way when they got to water? Why did they all react the same way? It was a chemical reaction. We took that element and we brought it near another element. Their outermost electron configuration is the exact same orbital, the exact same number of electrons, which means they all react the exact same. The families aren't just, they reacted that way, so it works that way. It's the electron configurations. Those are what are actually generating our families. That's pretty phenomenally cool. The periodic table has that embedded in it. For those of you trying to do the D block, stop. Don't worry about it. When we talk about valence, we're talking about ultimately either the first two, our S block and our P block. Those are the only ones we're concerned about. Okay? If you go through more chemistry, maybe at the end of 152, you'll hear something referred to as crystal field splitting theory. Okay? If you don't see it there, you take more chemistry and you move into a class actually devoted to inorganic chemistry, you'll run into crystal field splitting theory, and that talks about the D block and ultimately all of the colors that we see. Okay? Or some of the colors, the metallic ones at least. The metal colors that when you think iron, what color do you typically think of? Red for rust, iron oxide. Why is it red? It's the d orbitals. It's how the electrons are organized in the d orbitals. That's due to crystal field splitting theory.
What was that called again?
Crystal
Splitting theory.
That one. CFST. Okay? So don't worry about the d orbitals. You will only be concerned when it comes to valence for our S and P. Why? What are we going to use the valence electrons for? Bonding. And we look at bonding, we're concerned about how we bring those elements together. Why do we not look at the metals? Because that's a lot more complicated, and we don't want to worry about that yet. That's why. Okay? So, there's our valence. Periodic table gives you those organizations. We already kind of addressed those. This actually shows it, so the table does give you that, which is kind of neat. Okay? Let's go back to our atomic radius. Down a column, we had more electrons, right? Left to right, we have more electrons. And yet when we go down a column, it gets bigger, but when we go left to right, it gets smaller. Okay? Remember, I said the trend there had to do with the electrons and where the electrons exist. Where's the outermost electron for lithium? It's a bit disingenuous to show this periodic table. Use the periodic table on the wall. Outermost electron for lithium. It's in the second energy, S block, 2s1. Where's the outermost electron for cesium? 6s1. Okay, we're going to run through some clarity here because there's people saying 6s1 and other people kind of stumbling over it and they can't figure out the numbers. The people stumbling over it are looking at the screen. The people that are getting it right are looking at the periodic table. Okay, what is the problem with the screen? It's missing the first row. So if you're just counting them off, you'll be offset because you're missing the first row. Okay? So if we go through hydrogen 1, 2, 3, 4, 5, 6. Yeah? Why would it get bigger? Where's our outermost electron going? It's going to a higher energy level. So why should it get bigger? Well, the electron's going literally further away from the nucleus. That's why it gets bigger. What happens as we move left to right? Let's keep it really simple at first. Let's just do lithium to beryllium. What is the electron configuration for beryllium? Its outermost configuration. 2s2. So its outermost electron is going to which energy level?
Second.
The outermost electron for lithium was going to which energy level? Second. Those of you being like, aren't those the same? Yes! The electrons are going to the exact same energy level, which means how does the size change? I didn't ask about the nucleus yet. What would happen to the size if the electrons are going to the exact same energy level? It stays the same. Okay? Does it stay exactly the same? No, something else is going on. What's that something else going on? When we move left to right, what is also happening? We're getting more protons in the nucleus. More protons in the nucleus means I have a stronger magnet in the nucleus. If the electrons come in at the exact same energy level and aren't going further away, but I now have a stronger nucleus, it gets sucked in just a little bit tighter. And that is why when we move left to right, it gets smaller. Okay. I have a hard time memorizing trends, so I'm not going to say yes or no to that. Okay? So if we walk through the explanations that we had before, we said more electrons meant bigger. That worked down a column, did not work left to right. Okay? We tried, well, more protons meant smaller. That worked left to right, but not down a column. And that's because in both those explanations, we're only addressing a single aspect. It is not a single aspect that contributes to our atomic radius. It is two pieces of information. It is the energy levels and the strength of the nucleus. It is the competition of both of those that gives us our atomic radius trends. Okay? When it comes to atomic radius, you will be expected to rank a bunch of atoms. I'll give you 4 atoms and be like, rank them according to atomic radius. You should be able to go through and do that. Do you need to know this explanation to answer that question? Not at all. What do you need to know? You need to know the trend. So if you have the trend memorized, or you say, as soon as you get the exam where it has a periodic table, you write down the trend, all you have to do is use that information to answer the question. Okay? How can I get you to dig super deep into the electron configurations and look at this pattern? I have to ask a short answer question where you have to explain it to me. Okay? That's how it comes in. If you're like, damn, I don't want to do that, that's okay. That's not an A. That's fine. You're just deciding that you don't want an A grade. Does that make sense? Okay? Realize, as you move through a course, there'll be plenty of times where you're like, man, that looks like a lot of work. I don't want to worry about that. I'll just accept that as point loss. You only get so many times before accepting it as point loss is now not passing. Okay? Just so you know.
Which seems like it should be obvious, but people miss it over a period of 16 weeks.
Okay? Yes?
So will the question just be asking how we would describe the relationship and how things work, or you're saying it's the...
So to answer that
size
question,
of the
what I will say is, I know it's there actually, point to the practice exam and say, look at the practice exam, short answers, because I believe it's asked right there. So what you can do is look at that as a question to see how it would be formatted.
And the practice exam is a good representation of it.
Yes. Very good representation. How many people have looked at the practice exam? Good. The rest of you? You should probably do that. The exam is next Tuesday. Okay? That practice exam should be completed beginning to end by this Friday so that you can show me answers and I can tell you what you're getting wrong. Okay? I don't know how to answer that. Can you see it?
Yeah.
Then I have no advice, unfortunately. Okay? The next big concept that we need for Lewis structure is electronegativity. Okay? This one is a massive, massive concept that is so underplayed in Gen Chem that it is disturbing. Electronegativity explains like 70% of all of our reactions. If you understand electronegativity, you can pass all of chemistry, okay, when it comes to reactions. Because we throw a bunch of other random junk in there that is useful. Okay? But electronegativity does a lot. Okay? So what is electronegativity? It is the ability for one atom to take bonding electrons from another atom. So if I bring two atoms near each other, if one atom is more electronegative, it takes the other atom's electrons. If I just have an atom chilling on its own, electronegativity is useless because there's no other atom. Electronegativity is by definition taking it from another atom. Okay? The trend behind this, fluorine, oxygen, and nitrogen, okay, are the most electronegative elements. Okay? And we'll look at a potential reason for why-ish in a second. Cesium is the lowest. Why do we not look at francium or any of the noble gases? Okay. A lot of this electronegativity has to do with the desire to hold those more electrons. The noble gases don't react with things. The whole point of electronegativity is taking electrons from another atom. Noble gases don't react, which would mean there's no reason to evaluate an electronegativity. Okay? Why the bottom row? And for that matter, where the hell is the F block?
Because the electronic field is too large and can't let any more in, or it doesn't want to, or the power level's too large.
We haven't bothered to study them. Their reactivities are so high that we don't even use electronegativity as a measure for it because they're doing things like exploding instead of like reacting. Okay? So we don't evaluate them for that reason. Okay? There are a variety of ways to monitor electronegativity. One method was to balance ionization with electron affinity, and I'm like 90% certain that I, for whatever reason, deleted the ionization energy slide from this presentation. I will bring that in on Thursday, so it will show up on the exam, and it will be a new slide. Okay? Because that's helpful to discuss some of our electron configuration stuff. Okay? So, I said something about why they want those electrons. Okay? How many of you would like to be like a noble person, like nobility? If you describe the nobility, how would you describe them? has everything, which means lots of money, castle, fast cars, whatever else you want. How many of you would be like, yep, that'd be pretty cool. I'd accept that.
Yeah.
Like 2 of you. Okay. The rest of you are liars. Okay. All of our elements are trying to become like the noble gases. So let's take a look at fluorine. How could fluorine look like a noble gas? Okay. Well, what describes fluorine? What's that?
Said it's a non-metal.
It is a nonmetal, but I'm not going to write that. It is true, but not what I wanted. The 7 valence electrons. What else does it have? 9 protons. And I want to get rid of valence because valence is too specific. How could we change that? Instead of doing valence, make it all of them. So it would be 9 electrons, right? Okay. It wants to look like a noble gas. Describe neon. What else? 10 protons. Describe helium. Describe argon. I could ask you to describe xenon. What do you guys think? Is there any reason to describe xenon? Why did I pick argon, neon, and helium? Okay. What did we say fluorine wants to do? Be like a noble gas. Which noble gases did I pick? The 3 closest to it. Xenon is so far away to look like xenon, that's going to be kind of hard, right? So we're just, like self-made nobility, not like old family nobility. Okay, some people got that. I thought that was funny, but whatever. No. Okay, so what can fluorine do? Okay, it could add an electron. By adding an electron, what does it become? It looks like neon's electron configuration. What else could it do? It could add a proton. What else could it do? I'm not sure what double itself means. I see where that math was coming in. That was not where I was going, but that works. I'm not going to say double itself. I'm going to say, what do you think I'm going to say? Plus 9 electrons or plus 9 protons, right? Or? Everybody see all that? Like, damn, that's a lot of stuff going on up there. Okay.
Could it hypothetically become hydrogen as well? Or?
Hydrogen's not a noble gas.
Oh.
Ish. So, if protons, so which of those do you think is the easiest? Blue, green, orange?
Green.
Why green? Smallest numbers, right? You can do it all on one hand, not having to use multiple hands. Okay. Let's look at the proton first. If fluorine adds a proton, it's not fluorine anymore. It's now neon. This isn't trying to become the nobility. This is literally, you're going to become the nobility, but I'm going to kill you, and I promise you're going to be reborn as one of the nobility. Yeah, I don't know about that. Like, I'm pretty sure I'm not going to enjoy that. Pretty sure I lose my identity that way. So changing the protons doesn't work. Interesting. What did we say protons defined? The element. We can't change the protons because it changes the element. So the proton argument is now out of all of these. Okay? So now it's the electron argument. Which of those is going to be the easiest to do? Why adding one single electron? Least amount of work. To get 9, I got to find 9 electrons somewhere around, grab them all, and bring them in. Then I would look like argon, absolutely. But I got to find 9 of those little buggers. Or I just find 1. So what does fluorine do? It finds 1. If fluorine gains 1 electron, so now we get rid of all those because we don't need to worry about those, how many electrons would it now have? So it's no longer 9, it's now 10. What would its charge be? Right. I have an extra 1, right? So it should be a positive. I have an extra 1 of what? An electron, and electrons are negative. Remember how I said that negative sign is going to be a bane of your existence? Ta-da! Fluorine's a negative 1. That is why fluorine is a 1 minus. What happens with chlorine? It's just going to do one thing. It's going to gain 1 electron so it can look like argon. It's not going to gain math, 3617. You guys took too long. A larger number than 1. Chlorine to neon. It's not going to lose 17. It is much easier for it to gain just 1 electron. Okay? Well, that's just because that column is close to the noble gases. As soon as we move away from the noble gases, there has to be something else going on. Okay? It gets harder, right? Yep, it does get harder. I will absolutely grant you that. And because maybe it was just that top row, let's just jump in with sulfur. Sulfur has how many electrons? 16 electrons. Can we just ignore the protons now? Yep, that argument makes sense. What does it want to look like? It can look like argon or neon or, where is it? Krypton. To look like neon, what does it have to do? Lose a lot is pretty standard, right? -6. Look like argon. Gain 2. Look like krypton. That's an R. Gain 18? Oh, sorry. Totally looking at the wrong one. Which of those is the easiest to do? Gain 2. So instead of having 16 electrons, what are we going to have? 18 electrons. How many protons did it have? 16. What's its charge? Okay. Let's do one that's not on. Yeah, let's do one that's not on here. Let's do boron. Stupid text keeps popping up. Boron. What can we do? I can look like helium by doing what? -3 electrons. I can look like neon by 5 electrons. I can look like argon by gaining 13. Which of those is the easiest thing to do? Losing 3 electrons. Okay. What happens if we lose 3 electrons? How many electrons did boron have? 5 electrons. -3 electrons gets me 2 electrons. How many protons does boron have? 5. What becomes its charge? Guess what charge typically comes with boron? +3. We could predict that, right? Those of you being like, I don't know. Aluminum on here is a +3, right? What do we know about everything in the same family? Same reactivity. Look at that. Boron matches the reactivity. Wow. Okay. We could jump all the way over to the alkali and alkaline earth. Do the exact same process. What are you going to find? The exact same process works. Okay? One element on here, or one family on here, that I would argue you should not have to memorize. and we'll have some heated discussions maybe about that later, is carbon. Why would I suggest that we don't need to memorize carbon? What happens with carbon? If I look like neon, what do I need to do? Add 4 electrons. To look like helium, what do I need to do? Which is easier? Either one. Guess what happens with carbon? It can do anything from -4 to +4. All of them are possibilities. Why do we not make you memorize it? There's too many different things to memorize. We only make you memorize things that are always true. Okay? These are always true when we're talking about ionic charges. So ionic compounds. Okay? Because we all watched the play posit, we can now answer this fun little question. What is the charge on the carbon? You watch it and you're like, I have no idea how to answer that. Which is actually the appropriate response. Why is it the appropriate response? It would have to be an ionic compound. How do I know that that is an ionic compound or not? I would know it because metal and a nonmetal is an ionic compound. And carbon is, and oxygen is, not ionic. It's a covalent bond. Because it is a covalent bond, those charges are 100% irrelevant. Okay? This is challenging because we will see charges pop up for certain elements and we'll be like, oh, well, that one's a -2. And then another compound, you'll be like, why do I not know the charge there? It's because it's not an ionic compound. It has to be ionic for you to be able to apply those charges. Okay? So, in this approach, we've got some terms. We've got this term isoelectronic, equal electrons. Because how did we determine each of those charges? We looked at their electron configurations, and what did we do to it? We made them equal electrons to noble gases. Isoelectronic is coming from our charges. It's trying to look like a noble gas. That's why we've got our ionic charges. Neat. Okay? Other things that I want to add to this. This slide comes from your textbook, and it has some issues. Don't memorize those. Okay? You are required to memorize all of the charges that are up there right now. You are also required to memorize zinc, cadmium, and silver. Why would we require you to memorize zinc, cadmium, and silver? Because you will use them, number one. Number two?
There are memorized elements.
Why do we memorize them?
We're going to use them.
Not just because we're going to use them. Common's getting at it. How many different charges are there for zinc? 1. You are memorizing them because there is only one common charge. The zinc, cadmium, and silver are going to become a bit problematic to deal with the method we just walked through because they're dealing with the d orbitals. The d orbitals just monkey wrench everything. Okay? So zinc and cadmium will both carry a +2 charge. Silver carries +1. Nice try with +3. One way or the other, right? Okay. You are responsible for all of those charges. You need to know them. Okay. I would argue there's only 3 you have to memorize because the rest you can derive by knowing the isoelectronic term. Makes sense? Okay. What else could you do? Roman numerals become a bit dicey because we say 1 and 2, right? So +1, +2. Cool. +3, +5. Not quite.
It's like you're subtracting.
If you want to try and come up with some other pattern behind that, I'm fine with that. Just be careful that if you start putting too many patterns in the same position, you're going to start crossing the streams of that knowledge. Okay? So, how else could you do this? Well, you could memorize it without having to derive it. And you could memorize it for roughly 2 minutes. And then you could forget it. Wow, that's pretty cool. How could you possibly do that? Because you get the freaking exam, and at the top of each of these columns, you write +1, +2, +1, +2, +3, -3, -2, -1.
Because writing is how we store information.
That information is now stored in a random access memory device. Okay? You don't have to keep it in your brain anymore.
On the exam, we each get our own periodic table.
On your exam, you get your own periodic table. The practice exam that is posted is the exact format. Okay? So questions will change, but the formatting is exactly the same. Okay? It's a black and white exam, so I can't do colors. The people in the middle, again, are screwed, except I add another key to it that codes for the phases. Okay? So those of you trying to figure out and prepare for an exam, you should get the practice exam out and start working through it and use that periodic table. Get used to that pattern so that when it shows up on the exam, you're ready to go. And it's not relearning a new tool. Make sense?
Yep.
Cool.
It's like going into a parking lot and learning how to use stick shift before you go to the driver's test.
They don't even know what a stick shift is here.
Fair assumption.
Dane has life experience. He's got it.
Chapter 4. This is a summary of all the big topics from Chapter 4. Okay? So every time you see those names, I knew some people had to have had some experience. I hoped, to be honest. Those are all the big topics from Chapter 4. So you should be able to pull information from each of those. So when you see milliken, you should be thinking oil drop and electron charge. Okay, the exact electron charge. When you see neutrons, you should be thinking no. I'll kind of accept Rutherford, because Rutherford, by finding a nucleus, said that we had to have neutrons. Neutrons are mass. Neutrons are isotopes. Okay, so those are those big concepts that were embedded in with those. Right? We then get all our stuff about electrons. We then move to Chapter 5. Chapter 5 is a lot about periodic organization and trends. Okay? Ionization energy we'll come back to on Thursday. Okay? But periodic table, the predictions that Mendeleev was able to pull off. Not his predictions, but given some random data, can you make a prediction? Okay? Electron orbitals, how that follows in our periodic table, because that's our electron configurations. Chemical, physical properties, atomic radius, ionization energy, I said, we'll come back to on Thursday, and then our ionic charges. Kind of makes sense. Okay? If you've been following along, that should already be set. Okay? Which then takes us into Chapter 12, which is now talking about the types of bonds. I take different atoms, I bring them together, what kind of bond do I get? Okay? Right now, we'll have two classes. Okay? We have ionic bonds and we have covalent bonds. Why do we have two different classes for bonds? Okay? Metal and a nonmetal versus two nonmetals. Okay? There's still two atoms. Why do I need a new class? They react differently. There are characteristics about those classes that are distinctly different. One of those differences screams right out of the page at the beginning. Ionic bonds have metals. Covalent bonds are nonmetals. Okay? Are all covalent bonds the same? So H2O, hydrogen and oxygen, both of those are nonmetals. Hydrogen and chlorine, nonmetals. Do those compounds respond the same? Okay. One of my favorite things to talk about, okay, in OChem is something that I like to call the face test. Okay. If I splash it in my face, am I okay with it? If I'm okay with it, then that was probably an okay thing to go through and do as far as the chemistry was concerned. If I splash it in my face, what I'm trying to write down as far as my chemistry is concerned is probably wrong if I'm going to be like, ow, that hurt. If I splash H2O in my face, am I okay? If I splash HCl in my face, am I okay? No. Those are drastically different chemistries. Why are we not identifying them as different bond categories? I don't know why the textbook has decided to not classify them differently yet, but they are different. And we will talk about that probably at the end of the semester. Okay? So, ionic bonds. If we equate these to little kids, they don't share. Okay? They steal electrons. One atom steals electrons from the other. We're taking a non-metal and a metal. Where were our most electronegative elements? The top right, fluorine being the most electronegative. Which means our most electronegative elements are all non-metals. Our metals, our most metallic is the lower left, the least electronegative, which means when I bring a non-metal and a metal near each other, the non-metal will steal the electrons from the metal. Okay? Because it has now stolen electrons, it has gained electrons, which means it is now charged. It has gained a negative charge. Okay? Could it be -1? Yes. How did it become -1? It stole 1 electron. Could it be -3? Yes. What did it do? It stole 3 electrons. Okay? The metal, on the other hand, had electrons taken from it, which means it lost electrons. So now it should be negative because it has less stuff, right? Why is it positively charged? Isn't that actually gaining and loss of what? Electrons, which are negative. Okay. If we look at our cation, it loses negative charge. The result is positive. If we look at our anion, which I'm writing as N, don't ask me to explain that, is gaining negative, which means negative. Okay? Because of the regularity behind those charges, we get very crystalline solids. So most ionic compounds, their phases start as solids. It's very rare to see them in liquid or gas states. Okay? Okay. As soon as we move into the covalent system, we now see a big change in rules. Okay? Now we actually start talking about Lewis structures in bonding. These rules work every time. Okay? The most common reference for Lewis structure that I've seen out in academia everywhere is referring to atoms as Legos, and then you can do Lego brick connections with each other. That is phenomenal if you're a 2-year-old playing with Legos. Okay? Atoms are not Legos. They do not work that way. Okay? And anybody making the statement that they do has a fundamental misunderstanding of how molecules are made. Okay? Those same people sucked at OChem. Because what happens in OChem? How do you make molecules? Their understanding is so flawed they couldn't get through harder level chemistries. Okay? This applies to PhDs. Okay? I've seen plenty of PhDs that screw this up horribly. Okay? So, there's the rule set. These are the rules that you should follow. I know it looks like a lot. Okay? But if I showed you everything that we were going to talk about the entire semester on day 1, you probably would have said that was a lot too. Okay? But we don't do that. We slowly work our way through. Work your way through the rules. Okay? That's the point of them. Following them step by step. Notice we get lots of terms popping up that we've discussed. Those terms are relevant to explain how and why it works. Makes sense? Ish. Okay? The next big part that comes out of this chapter is once you have a Lewis structure, you can now explain something about its shape. Okay? For instance, if we take a human and disassemble it, head, torso, arms, legs. Okay? Just those pieces, we can't really describe the shape of the human until we start attaching the pieces. Okay? Once the pieces are attached correctly, we can now have a better explanation of the shape of a human. But we have to know how those pieces are connected. That's what this is. Okay? This is explaining that shape, but you have to have a picture first. What if your picture is wrong? Then all of this is wrong. This is why Lewis structure is so important. Okay? This, again, looks like a lot. It's about half of what you need, or it's half of what's possible. If you move into 151, they add in more stuff. We don't need to do the more stuff. We stop here. Okay? So, because we all watched the video, you've all seen CF4 and totally I totally know what that one is. We don't need to talk about it. What was that?
I think we should talk about it anyway.
Okay. Let's take a look at CF4. Total the valence electrons. Oh, I just realized what time it was. We'll do this fast. Carbon has?
6.
Try again.
4.
4, the Roman numeral above it. Fluorine has?
7.
7, Roman numeral above it. How many fluorines?
7.
4.
Or times 7. Or times 4.
7 times 4 is 28 plus 4. 32. There are 32 valence electrons. The center atom needs to be the least electronegative. Fluorine is the most electronegative, which means the center atom must be carbon. I'm now going to scatter the other atoms around it. Mother, just draw. It's just going to delete all my work. So there's our carbon with our center atom. I'm going to scatter the other atoms around it. One of the simplifications we made within this is that we're looking at tetrahedral, 4 groups. What shape has 4 sides? Square. Put a square around your center atom. Where should I place the fluorines? Faces of that square. This is why the square is there. Right? Fine? Yeah. Electrons. I now want to place the electrons into my drawing. I will place them on the most electronegative element, which is fluorine. Which fluorine? Doesn't matter which one I start with because they're all the same. I'm going to start placing them first in between because I have to make a bond, so it makes sense to do that. How many electrons? 32. How many did I say I needed? 32. Everywhere there's a pair of electrons between atoms, I will turn into a line to represent the bond connecting them. Right? Satisfy octets by moving pairs. So I will look at each atom and say how many electrons are around it. Fluorine. 1, 2, 3, 4, 5, 6, 7, 8. Okay? Carbon. 1, 2. They all have 8 electrons around them. Yes. What does that mean? I'm done. That was it.
Okay, real fast. I know we're over. Thursday, your final project 1 is due.